You must take your attendance first, as usual. Senior teams. Okay, so let's we start. Last lesson for the quantum. Okay. Go back to the slide. As usual. Okay, so we're supposed to discuss this. About energy level. Okay, so far we are talking. So what you learn so far? First thing you learn about what? Photon. What is photon? Cuma packet of energy of EM radiation. Okay. An initial idea about light. Okay. Not say light, about EM wave. Okay. After you learn that, what is that? Photoelectric effect. Okay. What is photoelectric effect? Cuma emission of electrons from a metal surface. EM radiation is three evidence against this theory. Right hand side, please. What is the three evidence? Three outcomes that against this theory. First, the emission is instantaneous. Second, the existence of what? Threshold frequency to release the electron. Third, the kinetic energy is found to be independent to intensity. Okay, it looks like it's dependent to frequency. Okay, then after we learn that, I started explaining the formula. Okay, HF equals to work function plus EK. Work function can be transformed to what formula? Work function HF naught. Kinetic energy can be transformed to what formula? EVS or EV naught. Elementary charge multiplied by the stopping voltage. Okay. So then, yesterday we talked about de Broglie. What the contribution of de Broglie? Is it a new idea called wave-particle duality? Wave as a particle nature, particle as a wave nature. Okay. What is the proof that wave has a particle nature? What is the proof that wave has a particle nature? What experiment? Photoelectric effect. Photoelectric effect is proof of what? Wave shows particle nature. Okay. What is the proof that particle shows wave nature? Electron diffraction pattern. Okay. Electron diffraction pattern is the proof of what? Particle shows wave nature. Electron shows diffraction. Diffraction is what? It's a property of wave. Okay. So particle shows wave nature. Okay. So de Broglie introduced the controversial relation wave-particle duality. Okay. And what is the formula introduced? Another weird formula. First time weight linked to the momentum. What is that? Lambda equals to h over p. Okay, lambda equals to h over p. Very important formula. So any momentum, any particle. So what is the consequence of that formula? Lambda equals to h over p. So the formula tells that is the wavelength associated to a particle which possesses a momentum of p. Okay, that's the consequence of that formula. Okay. What is the consequence of that formula? Lambda equals to is the wavelength associated to a particle which possesses a momentum of p. But that formula only works for one particle so far. What particle? Electron. Okay. So far it works for electron. Other proton source, they believe that it has a wavelength, but they can't see the diffraction pattern. Okay. Only electron able to observe the diffraction pattern. Why? Because wavelength, the electron has a wavelength is quite low or very large. Very large, significant to show the diffraction pattern. The others no, we all can't. But according to that theory, believe that you all have a wavelength. You yourself has your own wave character within you, but you can't show it because your wavelength is too big or too small? Too small. Because you have a huge momentum. Because you have a huge momentum. Okay, that's the problem. Okay, then after we talk about de Broglie, then came in atomic structure solved by quantum physics. Quantum physics, atomic structure. Rutherford model about a problem. Then Niels Bohr explained the electron should have an energy level, and the energy level formula, the energy levels was getting closer and get further. Okay, the ground state is the what is ground state? Another question to ask. What is meant by ground state? Is the lowest energy level can be occupied by an electron. Okay, ground state. So the ground state is the energy level is quite close to nucleus. The energy is highly negative. Okay, the energy is highly negative. Okay, so today we're going to proceed from there. Okay, this is the last part already, Niels Bohr, but we're going to show what is the proof behind it. Okay, before we do that, we try one question about the energy levels. Okay, so recall back, there are two type of line you have to draw. Okay, be careful when to draw the arrow down or up. Okay, when you draw the arrow down, when the electron transiting down, when they say draw a emission spectrum. Draw an emission spectrum for an electron. When they say emission spectrum, means in your mind you must say emission of photon. When electron can emit photon and go down or go up? It goes down. When it goes down, the energy emit become photon. So emission spectrum. The emission spectrum arrow goes down. Absorption spectrum, electron absorbs photon, goes up. Absorption spectrum. Absorption spectrum, emission spectrum. The other day I showed you, if you have 4 energy levels, you should know how many lines you need to draw. Start at the top, then 4, and I say you got 4 energy levels, 4 to 3, 4 to 2, 4 to 1. Okay? Then from 3, 3 to 2, 3 to 1. And 2 to 1. And you should know which is the longest wavelength, which is the shortest wavelength. Here, which should be the longest wavelength? The photon emitted which has the longest wavelength. The one with the least energy or the most energy? The one with the least energy, right? What is the photon energy formula? E equals to HF or HC over lambda, right? The energy is inversely proportional to the wavelength, right? So which has a big wavelength? Sorry. Here, very difficult to tell. Should be, no. You only can find longest. Shortest should be somewhere here. I'm not sure. Okay. So the longest here we can get the shortest wavelength. This should be the shortest wavelength, right? That's the greatest energy. Okay. Big energy difference leads to the greatest energy, smallest wavelength. Okay. The shortest, the least energy should be the transition from the infinite to the one energy lower, small energy. That releases very little energy and longest wavelength. Okay. Okay, when this transition can happen? when the electron receives photon, when the electron receives energy, this absorption can happen. Okay, how electron can receive energy? From light, from heat. Then third is what I told you, collision of incoming electron. Another electron which is fired from the maybe electron gun, hit the metal plate, and the electron incoming electron will collide with this orbiting electron. This orbiting electron can get some energy. Yeah, and it can expand. Yeah, so you use. Okay. So now this question. This. Yeah. Okay, look at this question. Try to understand. Okay, so for energy levels for this atom, the lowest energy level is negative 13.6. So far, science for nil Bohr idea, the only atom that's been investigated, the energy level is hydrogen. Okay. Other helium, the energy level looks a little complex. Yeah. Only hydrogen. So hydrogen, the ground state of hydrogen is thought to be 13.6 eV. Yeah. So means what? You want to ionize this electron. How much of energy the electron should receive? To ionize the electron. 13.6 eV. You apply 13.6. Like as your escape speed last time, you want to escape from the Earth. What is the energy required? The potential energy you have now, right? Highly negative. So this is the potential energy of the electron at this point. Yeah. The energy required right electron. So first, what is the ionization energy of the hydrogen atom? 13.6 eV. The energy at the ground state. Okay. So 13.6 eV is the ionization energy. Okay. Some atom, the value might be greater. Okay. So the first answer, the ionization energy is the energy at the ground state. 13.6 eV. Okay. Okay. Okay, done. B. What is the minimum frequency of the photon that is required to cause an electron, the ground state of hydrogen atom to be ionized? So how do you calculate that? What is the minimum? What is the frequency required? What is the frequency required? The electron receives a photon. How much of frequency of that photon needed for the electron to release? So that photon should have how much of energy? 30.6 eV. So 30.6 eV equals to what? What is the energy formula for photon? Hc over lambda or Hr. What do you use here? Because they want frequency, use Hr. So Hr equals to what? Hr equals to 13.6 eV. But do you leave it as eV? You have to change to joule. Okay, Hr is joule. How to change eV to joule? Times with elementary charge, right? 1.6 times 10 power of negative 90. Okay. So 13.6 times 10 power of 13.6 multiplied by 1.6 times 10 power negative 19 is the energy in joule. That equals with what? HR. So you get the answer for the B. Okay. So this is working, right? You got 30.6 is the minimum energy. So minimum frequency, E equals to HR. So E over H. E, the 13.6 multiplied by the elementary charge, change to joule, divided by the time constant, you get the frequency. You will release the electron. Yeah. Come back to this. Okay. Maybe A is something new you learn. Yeah, the ground state energy is the ionizing energy. Yeah. B, I expect you to know. E equals to HR, you find the frequency. Yeah. But the main focus of this question, what I'm asking you to do is the CE, something different. Okay, look at C. Okay, what C say? Read the C. Figure out what do you think the answer should be. What would be likely to happen to photons of energy 12.75 eV and 15 eV is if they pass through gaseous hydrogen atom in the ground state? So all two photons have been received by the ground, exposed to the electron. Electron getting two photons. One is 12.75 eV, 15 eV available. Okay. Maybe 12.75 eV, maybe blue color, 15 eV, violet eV. So two photons are come to the electron. So question is, what would be likely to happen to the photon? Likely means, is it the electron will absorb the photon or it won't absorb the photon? Which photon it will absorb? Which photon it won't absorb? And why? Which one do you think it will absorb? You take 12.75, 15 or take both? So, what I told you, electron, is it take all the photons? You just take the specific photon just enough to go to the next energy level. Okay? So, from here, if you take 12.75, can you jump any energy level? Number 3, yeah? Is it 13.6 minus 1.5? 0.85. 0.85. So 30.6, 0.85. Yeah? So which one? 12.75, right? So 12.75 temporarily the electron will absorb. Okay, it takes the 12.75 of photon, the electron will jump to E form. Yeah. So 12.75 will be absorbed by the electron and it will transit from E1 to E form.
It's gaseous, right? So it might miss. Wouldn't it miss all the electrons?
It will miss all the electrons.
It's gaseous, right?
It's gas state, yeah.
We can't write that, right? We don't have to say that, right?
Because too many lights expose the gases, hydrogen is in form of gas. You have to be in gas, so that particle will focus on. Okay. So 12.75 definitely will absorb. How about 15? 15 you don't absorb. You just take the specific photon. Yeah. So 12.75 will be absorbed. 15 eV. What happened to the 15 eV? Just escape from the hydrogen atom without absorbed by the electron. That means if you shine, let's say 12.75, you shine with, let's say it's a blue light. You shine the blue light through the hydrogen atom. Yeah. This is 12.75 blue light. Blue light transmit to the hydrogen atom. After that, no light will be emitted. All the blue light photons will be absorbed by the electron to go out. Okay. Let's say 15 is a ultraviolet. Let's say it's a violet. Violet is then pass through the hydrogen atom. The violet light will be emitted because it never absorbed. Electron never absorbed. Okay. So 12.75 will be absorbed. Okay. So the answer expected is 12.75 is absorbed and it jump from E1 to E4. 15 eV won't be absorbed. Okay. Very important thing we learn. Yeah, just take the specific photons, which enough to jump to one level to another level. We never take more, we never take less. Yeah. So that's the case for photon. Yeah. D, another one. Okay, D. D is a different case. Yeah. Read the D. The bombarding electrons of energy 5 eV, 11 eV collide with gaseous hydrogen atom in the ground state. This is now the electron, the initial electron getting energy from a colliding electron. Another electron come and collide. Okay? And that electron has an energy of 5 eV and 11 eV. It has a kinetic energy of 5 eV. Okay, here, it's not like a photon. Photon, either you take the entire energy or you don't take the entire energy. But for colliding case, the electron can take the amount of energy required from the electron and jump up. That means you don't need to take all the 5 eV. You can take a fraction of 5 eV from that electron. Okay? So 5 eV, can it jump anywhere? Not even the first level. So the 5 eV electron when they collide, this electron, it won't take any energy because not even 5 eV, it can't even jump the first level. So the electron, incoming electron with 5 eV will move away from the atom with 5 eV. It never loses any energy. Okay? So 5 eV, electron of 5 eV will be escaped from the hydrogen atom without losing any energy. Okay? How about 11 eV? 11 eV, you can jump where? Can you jump here? 13.6 minus 3.4, how much? 10.2. 10.2, right? This is 11. Here, figure 12.1. Right? So, the 11 eV afford to make the electron to jump from E1 to E2. Okay? So, what will happen? The electron will take about how much from this 11 eV? 13.6 jump to 3.4, how much? 10.2, right? 10.2. So, the electron will take 10.2 eV from the 11 eV electron, okay? And the orbital electron will jump from E1 to E2, okay? But how much balance the electron has? And they go in 11 eV already give up 12.2, so it left with 0.8 eV. So that electron will come up from the hydrogen atom with 0.8 eV. Okay. So try to understand the difference. Photon either it takes the entire or it doesn't take. But incoming electron colliding, the orbital electron can take as much as it wants to jump. Okay. So how much energy is absorbed by the gaseous hydrogen atom electron in the ground state? So how much? 11.2 eV, right? 13.6 minus 33.4. 11.2 eV absorbed. How much energy is retained? The bombarding electron? 11 minus how much that? 10.2. So 0.8. 0.8 eV is retained. Yep.
5 eV is
The 5 eV never lose any energy will be retained. How much energy is retained? How much energy is retained by the bombarding electrons? Yeah, 5 eV is retained. 0.8 eV, 8 eV is retained for 11 eV. Okay. Okay. So the highlight of this question is the C and D. That's why I'm giving this question. Okay. And last one, E, I think I expect you to know. Come on, people try E. If a hydrogen atom is in the energy level of 3, the electron is at N3. Show all possible transitions that the electron can undergo on the diagram and find the corresponding frequency of photon that are emitted or absorbed during the transition. Okay. E, I want you to draw emission spectrum. Draw the emission spectrum and the electron at N3. Draw the emission spectrum and the electron is at N3, third energy level. Emission spectrum. Emission spectrum means the electron emit photon. When the electron can emit photon, goes down, when it goes down or goes up. When electron emit photon means it releases its energy, right? So when it happens, when it goes down. Draw emission spectrum means arrow goes down. Emission spectrum, the electron loses energy, emit photon. So draw the possible transition from N3. So the electron is at N3. They want you to draw the transition at N3. Electron is N3. It's going down. So 3 to what? 3 to 2, then 3 to 1, right? One type. Another one is from the electron which is jump at 2, chance to go to 2 to 1. here, emission spectrum, right? Yeah. So electron at 3 can jump to 2, can jump to 1. Like I told you, like stairs, the ball drops down. Okay. So the ball is the electron. So for many ways you can use this energy. Okay. So the first one maybe jump at 2 and 1 by 1. Maybe the electron at the 2, because already dropped to 2, can jump to 1. Right? Give us another. Okay, so now the question is, find the corresponding frequency of the photon that are emitted and absorbed during the time. Okay, let me define the frequencies. What I want you to know, out of these three, which is the shortest wavelength? 1, 2, 3, which is the shortest wavelength? Yeah. Okay, this is 1, this is 2, this is 3. Which has the shortest wavelength? 3 has the shortest wavelength. Is it 3 as the shortest wavelength? 2 as the shortest wavelength, right? 2 as the shortest wavelength, largest frequency. Which has the longest wavelength? Which has the longest wavelength? 1. 1 has the longest wavelength. H over lambda, energy inversely proportional to wavelength. So less energy will lead to greatest wavelength. Yeah. Energy level. Okay. So important main mistake students do is the arrow direction. Instead of when they said absorption spectrum, the arrow is supposed to be upwards, they draw downwards, so you lose mark. Okay. Emission spectrum arrow is downwards. Absorption spectrum arrow upwards. Okay. Okay, so this development is totally from quantum physics. Okay, Niels Bohr derived it by using the de Broglie's idea, lambda equals to HOP, and he got these energy levels which getting closer. Okay, but purely theoretical, but need to have proof to accept this idea. Okay, why this idea first of all arises? Because Rutherford model has a downfall. Because charged particle when accelerate loses energy. It should eventually fall to nucleus, but that doesn't happen. So new model was what you call proposed by Niels Bohr, but it was proven. The proven, as I told you, is what? Line spectra. Okay, what is this? What is this line spectra can prove the energy level? This is the energy level. Okay. This line spectra is actually the wavelength they obtain from emission spectrum and absorption. This is actually the emission spectrum and absorption spectrum wavelength. Okay. Okay. When emission spectrum happens, when the electron goes down, right? The electron goes down, it's called emission line spectrum. Emitting photon. This is the emission spectrum they got. And absorption spectrum, when what are the wavelength the electron absorbs when it absorbs, goes up. Okay. Okay, how they got this outcome? What is the setup looks like? So this is the setup. Okay. This is the setup to obtain the emission line spectra. Emission line spectra means the electron goes down, releases wavelength, right? So when the electron was in the metal plate, whatever metal plate or gas, here they use gas. Heated gas or low, right? Heated hydrogen gas, they heated it. So why they heated it? First of all, they want all the electron to go to the excited state. They go to the excited state. Okay. Then the heated gas was just leave it here, okay, in a dark room. They leave it in a dark room. Okay. So what happened? After a short while, maybe after 2, 3 minutes, maybe 5 minutes, let the electron go down. Take that's how you show the level 3 or 3 type of transition, right? 3 type of transition, 3 wavelength will emitted. Okay. So from this hydrogen atom, the excited electron will go down, release wavelengths, and that wavelengths will be focused by using a lens and sent to the prism and directed to a photographic plane. Okay. The last time we send a visible light, it changed to 7 colors, right? Yeah, by using a photographic plane. Yeah. So here, use the same setup, but you get one wavelength, which is here. You know, top is break down as well. You see each color is strikes. Yeah. So if here, okay, let's say I go just now 3 energy levels. Let's say this hydrogen gas. Let's say I got 3 energy levels. How many possible wavelengths must be emitted? If the hydrogen got 3 energy levels, 3, right? 3, right? I got 3, right? So if Delco correct, only 3 marks, 3 wavelengths should be obtained. Okay. So they check, but first of all, they don't know how many hydrogen energy levels inside hydrogen. Okay. But let's say they got 3 energy levels. Still cannot overlay normal price because how we know there is only 3 energy levels? Because they are got infinite, right? Can get closer, the energy levels are get very close, got lots of energy levels. Okay. So let's say they got 3, let's say they got 3. But if Nilco is correct, this is emission spectrum, emitting photon, and the electron goes down. Okay. Now they do absorption spectrum. Absorption spectrum means what? Electron all at the where? At the beginning. The electron all have to be at the ground state. So we send the visible light, whatever all the wavelength. Only the 3 specific wavelength which are emitted here need to be absorbed, right? The 3 which is emitted here. Let's say 400 nanometer release here. That means the energy level is equal to 400 nanometer, right? Later when you go absorption, send the light, all electron ground state. When you send the light, visible light, the 400 nanometer should be absorbed by the electron, right? So when the visible light, which is rainbow color, reach the prism, pass the prism, you're supposed to get the rainbow colors, but the 400 nanometer should missing because the electron already absorbed that photon, right? So when rainbow correct, if here appears 400 nanometer, but the absorption, the same wavelength is missing, identical, then it's correct, right? So emission light spectra, okay, passing the light emitted gas, okay. The light is separated by different frequencies, show color lines, yeah, electrons in the excited state falls back to the lower energy level, do emission spectrum, okay. So now they do absorption. Absorption, cool gas. Why they use cool gas? They want the electron to be at the ground state. Okay. So they use a lamp which keep up a visible light 400 to 700. All the wavelength is available to the electron to select what he wants. Okay. But we know the electron only can select a specific wavelength, right? If Nilco is correct. Okay. So when they stand here, what happened? They supposed to get rainbow color here, but some wavelength is missing, right? Because electron take that specific wavelength to go out. Okay. So see the outcome here. This is the picture. This is what the emission spectrum they obtain. Hydrogen gas. These are the lights that have been emitted by the electron when it's in an excited state. First one is hot gas or cold gas? First one is the hot gas. The electron all in an excited state. And the electron comes down, it releases this specific wavelength. This is a photographic plate at the side. It's a specific wavelength. So these are the specific energy level in ESCOM. Let's say this is 800 nanometer, so you should understand that the energy level from one to another energy level, one specific energy level, the photon it comes out as a wavelength of 800 nanometer. Okay. So when they do absorption for the same hydrogen atom, because the background is rainbow color, the spectrum, the same wavelength which appeared here was missing. Okay, so it's proven. That means electron has a specific energy level. Okay, so it's a clear evidence that Delbo's idea is correct. Okay, you got a double price for this. So proof of electron as a discrete energy level. What is the proof? Line spectra. Okay, line spectra is the proof of existence of discrete energy level for light in that. Okay. So emission spectrum, absorption spectrum. In exam, they'll ask how the emission spectrum looks like. Emission spectrum is a discontinuous colored line with a dark background. Emission spectrum. Okay. What's the absorption spectrum look like? Discontinuous dark line with colored background. Okay. But the weird thing is, all this thing which is critical, unable to identify by the classical physics, was revealed by quantum. Okay? Quantum physics able to give very important solutions, where in some science we unable to explain. The Rutherford model we are unable to explain, but quantum able to explain, and it was proven. Okay? Purely theoretical, but when do experiment, it was proven. Yeah. Photoelectric effect, we thought light is a wave, it is a wave, but when interact with matter, it looks like the energy is in a packet. So quantum idea is used to explain. And when Millikan do the experiment, he found that what Einstein says is true, and more people start to believe to quantum physics. Quantum physics was become more relevant. Yeah. So you can see some the Avengers movie, they use the quantum idea to go for the time traveling. Yeah. Very futuristic idea. Can't. So far not implemented. Yeah. Okay, so line spectra, emission spectra, absorption line spectra. Let us solve about this topic. Okay. So this is what quantum physics.
Sir,
Yeah.
can explain the setup again?
Setup, Okay. Still. Setup got what? Emission spectra and emission absorption, right? Emission means you have to know the electron emission when electron do emission spectra, when the electron goes down or goes up, and the electron goes down. When it goes down, it give out emit photon. So this is the emission photon. So electron must go down. Okay. So for the electron to go down, originally, what type of gas need to be used? Must use hot gas. Why hot gas? So that initially the electron is at the highest state. They have to be at the highest state. So you use a hot gas. So hot gas, when you wait for a while, what happened? The electron slowly will transit to, if you got 3 energy levels, the electron will transit 1, 2, and 3. So 3 different type of wavelengths will be emitted from the hydrogen gas. Okay, these 3 wavelengths will focus to the prism and photographic plate. So the photographic plate will show 3 different colors. Okay, it shows 3 different colors, but the background will be dark, of course, because only 3 wavelengths emitted. So this is called emission line spectra is produced. Okay, so we use a hot gas. Okay. So for absorption, of course, absorption means when absorption happens, when the electron from ground state absorbs energy goes up. So initially the electron have to be ground state. For the electron to be ground state, the gas have to be at a low energy level. When it need to be at a low energy level, at a low temperature, so the type of gas we use is a cool gas. We use a cool gas so that electron all are at ground state. So we shine a light, you need to get wavelength, you need to get energy. So we shine with the visible light which has 400 to 700 nanometer of wavelengths. let the electron pick the specific wavelength it likes. Okay. So when the light passes through here, the electron will only take the 3 wavelength it releases earlier. Okay. So what happened? You will get the rainbow color, but the 3 wavelength will be like missing. Okay. So that's absorption spectrum. Okay. So because these two are matches each other, the one which found in the emission, it was lost in the absorption. It matches. So therefore, the Newell-Boss idea is proven correct. Okay.
Okay.
Okay. Let's do some questions. That's the. Yeah.
What was that experiment trying to prove?
The experiment tried to prove the idea of Newell-Boss, because Newell-Boss said that electron has specific energy levels. Okay, only this proving that, right? Only if you don't have specific energy levels, I think if you don't have specific energy levels, what is expected here? What is expected here? If you don't have specific energy level, you can go any level you like. Means the entire spectrum should be absorbed, right? The spectrum can go any level you like. We absorb all the light. Okay? Because now electron only got specific energy level, you only take the specific wavelength. Okay? So to prove Newell-Boss. You know, this line spectra is unique for every type of what do you call atoms. You know, let's say they want to find they got a mineral from some mineral weird mineral from a different planet. Okay, so they shine the light. Let's say you don't know what is contains inside. They shine the light. They see this emission absorption spectrum. Okay, to identify what type of mineral is that. Okay, different mineral will have a different energy level. It has its own line spectrum. Okay, so for aluminium, it has its own line spectrum. So when they shine the mineral, the unknown mineral from that planet, they shine this light. They check the line spectra. From the line spectra, they will tell you this mineral contains this element, this element. Okay, use of line spectra. Okay. Look at the questions. Oh, sorry. Go to the questions, pass here. Okay, just selective questions. Okay, this one. Okay, about line spectrum. Okay, so one part here. Figure it out. First question, fill the table. 3 lines observed in emission spectrum. Emission spectrum means electron goes down or up. Emission, emitting photon. So electron goes down. So 3 different type of wavelengths emitted. 656, 486. So they are asking what is the energy content for 486 of wavelength. So what formula do you use? 486 of wavelength. How much of energy of possess the photon? What formula do you use? Hc over lambda. Okay. Photon energy only. Okay. So formula to be used to calculate this energy is Hc over lambda. Planck constant times speed of light divided by the wavelength. Okay, we get the energy of a photon. Wavelength change to meter. 486 nanometer change to meter. 489, you get the energy. Okay, so part A, of course, formula is what? Energy is Hc over lambda to be useful. The Planck constant, speed of light, 3 times 10 power 8 over the wavelength. 486 times 10 power negative 9 to be used to get the energy in terms of joules. Okay. Right. Okay. Next. Okay. So 2.2 partially completed diagram to show energy levels of hydrogen reactor. Two levels have been shown here. These are the energy levels. Yes. From here to here, they say the wavelength emitted was 656 nanometer. Yeah. We only show two energy levels. Yeah. So what's the question? Okay. So draw one further label energy level and complete the diagram with arrows to show the energy changes for the other two wavelengths. Can you add the third energy level in this diagram so that you can show the other two wavelengths? I go back to the table. This table is what wavelength? 656. Remember the wavelength. 656, 486, 1880. Three wavelengths emitted. 656, 486. Okay. So we go back. The one shown here is 656. So you need to draw the 1880 and the one longer wavelength than this and shorter wavelength than this. So we draw the third energy level. Up or down in between. Up or in between. We're going to get another two wavelengths, right? One should be longer than this. One should be shorter than this. If you draw in between, yeah, can you get the both? If you draw in between. Because, or you put on top. Let's say you draw in between. Let's say you draw in between here. You draw one energy level here. Okay. What is the possible transition? From here to here, right? One. Here to here, right? Or here to here is already shown here. Another third one is where? From here to here, right? Okay. Can this the first one we draw on top, is it more than 656 or shorter than 656? The one I draw here. More than 656 or shorter than 656? More. Should be more, right? Because less energy, big wave. Yeah? How about this? Is this going to be more than 656 or shorter than 656? It's also more. So both going to be wavelength which is greater than 656. But you want one wavelength shorter than this, right? So if you want one wavelength shorter than this, the energy level must be big, right? So where do you draw? Here or up here? Should be on top. Okay? So the energy level should be on top. So this is not the energy level. Okay, so energy level, the correct one. Okay, so this is all wrong. So the energy level must be on top. Okay, so draw one energy level here. Now makes sense. Okay, this energy level, one is here, another one is going down, right? Makes sense. The first one should be what wavelength possible? Which wavelength? 486 or 1880? The one. This one. 1880, right? This one is the second one here. This is the smaller one, for what? 418. 486. So this should be 486 nanometer. What energy level you need to write here? What energy you need to write here? The energy level. So the energy level you need to write here is the which energy on top. Which energy? Be the 486 one, right? 486 is the biggest energy transition. So whatever answer you got for the part A is the answer here. So whatever answer in part A is the energy here. You need to write that energy.
So why is the 486 energy?
Why 486 nanometer?
No, why is the energy the 486 nanometer?
Why the energy is 486
But what is the energy supposed to be for the?
486 nanometer is the shortest wavelength, which yields the greatest energy, right? So 486 from this energy to this energy is the ground state. Yeah. So 486, this energy differences is 486, right? So this energy differences, so this is 3.03 times 10 for any ranking. So this should be, this 3.03 is the exactly this value. It means the ground state take to be like 0 in this case. So we exactly take this value as 0.6 energy. Okay. Any questions? Yes. Any part you don't understand? Okay, so new idea, energy levels. Okay. Going up, electron absorb, lose photon. Going down, release electron. Okay. Proof is what? Light spectrum. Okay. How Nielberg got this idea from de Broglie. Okay. What de Broglie said? Wave particle duality. Okay. So this topic tells that wave and particle there is some sort of a relation. Okay. Particle as a wave character and wave as a particle character. You as a particle do have wave character according to them, but not very significant for you because you have a huge momentum. You have a huge momentum. Okay. The wave only shows its particle nature only that one experiment, photoelectric effect. If you don't have photoelectric effect, I think this entire topic won't be available now. Okay. All because of that photoelectric effect, but very helpful because we solve the atomic structure. Yeah, the main thing is the atomic structure, solve the atomic structure. So after the discovery of this energy level, what quantum physics gives us? It gives one important contribution to us is what? What is the contribution of quantum physics to us? We are using daily life, very useful substance, laser. Okay. Laser is from idea of quantum physics. Production of laser is using the energy level, okay, the energy difference level. Okay. They have to what you call the substance they use, they have to make the electron to go to the higher energy level, and it comes down, it releases the red light. Okay, that substance. So the idea of quantum physics is used for the development of laser. Okay. So laser is a very important uses, right, for us, barcode. Yeah, many because of very what do you call high intense monochromatic source. Yeah, so yeah, so we stop here. So tomorrow will be your test. So first 1 hour I give you test. Okay, so the test I put in the questions, the times. Okay, no contact lah. So you write down, you scan the answer, you upload it into the times. Okay, you have to upload it into the times. Like last time, right? Exam. So I'll put it in times. Okay. So you get the question paper in times. Okay. You write the answer just in a piece of paper. Then you scan it by using a cam scanner. You have the cam scanner, right? Scan it, change to PDF, upload it back. You can upload. I show you where to upload. Because my previous class they know. So okay. First 1 hour. Yeah.
For physical, if I'm coming tomorrow, will you give the physical paper?
No, physical also we go like the paper will be like given in the times. You just sit in the lab and do the question first.
Oh, so must bring my laptop and everything.
Yeah, better bring your laptop lah. Laptop, or you like okay with your phone, then access with the phone, whatever. Okay. Okay then. First 1 hour. Thanks. And the second 1 hour we go back to the D4. You're supposed to finish your D4, right? C we hold on first. We've done a lot of C already, so we go for D4. Let's be set. Okay. Thanks. Any questions? No questions, guys. Okay then. See you back. Thanks.